So this video is about finding the angular momentum of a gyroscope. So we know that for any rigid body, you can use the angular momentum being split into the spin angular momentum about the center of mass and the orbital angular momentum of the center of mass about the origin. You can always do that. So here's a little description of that. So we know that angular momentum L vector is given by summation of mi and then ri cross vi about origin, and this can be written as m r naught cross v naught, where r naught is the position vector of com and v naught is the velocity of com about the origin, plus this other term, so it's summation of mi ri vector cross so this symbol is just the relative velocity of the ith particle as seen by the center of mass. I will also call this vi, but to distinguish it from the vi as seen from the origin, I will write it in this fancy fashion, right? So this is very well known and it is used a lot. It's used a lot in the analysis of planar rotation, right? It is used for wheels and gyroscopes and things rotating in a plane, and yes, many other things. But this by itself is not sufficient. So for the complete 3D analysis, it's not sufficient. You need something more. Okay, so let's continue. Call mr naught cross v naught as L naught. So it's just nomenclature. I'm just defining L naught vector as the mr naught cross v naught term, and the other term is just L1 vector. So you can write it like this. And then I give the description of L naught vector and L1 vector physically, right? So this is very easy to use for planar motion, but for 3D motion this can get difficult. So we are considering as our gyroscope, we are just considering a thin plate which is rotating about this r naught vector, and the r naught vector is itself rotating about the z axis with an angular velocity psi. So psi is just d phi upon dt, where phi is the angle made with the positive x-axis by the vector r naught, right? And theta I, so I represents the index of the particle. So instead of naming the particles, I'll just refer to them as their masses. So I'll just call mi, and yeah, no big deal. So let's consider the case of thin plate rotating about an axis about itself. So I described that, right? So here's all the terminology. So psi is just d phi upon dt, and omega is d theta I upon dt, and this is for every single I value. So for all the particles, their theta I is increasing at the same rate. So now we'll use this equation that we formed once again, and we can write this as mr naught squared times psi. So that's the first term, and we can use the fact that since the center of mass is just going around the z-axis, you can write this as mr naught squared times psi vector instead of using the velocity vector, which will change with time. So you can just write it like that. Fine. So this thing doesn't change with time. Yeah. And the second term is just mi ri vector cross vi vector, so the relative velocity vector, right? That's little difficult to calculate right away. So for that, first of all, we'll consider what ri actually is. So we will split this into its coordinates. So this can be written as ri, which is just the magnitude of this ri vector, which is also constant because rigid body, right? That times sine theta I z hat plus cosine theta I t hat. So here I have just split this using this triangle, so you can see the triangle, right? Yes. So t hat is just a tangential vector which is shown over here. So it's tangential to this whole body. I mean, it's basically tangential to the path of the center of mass, but I'll just call it t hat throughout. So it's perpendicular to r naught vector. It's basically like you rotated r naught vector anti-clockwise by 90 degree, and yeah, you just get t hat, right? So I decomposed ri vector into its components along z hat and t hat, and since it's just a thin plate, there's no component along r naught hat, right? And then I differentiated this. So this is easy. I mean, z hat is just a constant, but then t hat is not a constant. You have to differentiate that as well. And then doing the usual thing, so writing t hat in its xy components and differentiating, yeah, you just get that the derivative of t hat with respect to time. So don't get confused, t hat and t are completely different things. T is the time and t hat is a unit vector. So the differentiation of that thing with respect to time, that just give us negative psi times r naught vector. This is not supposed to be dot, it's just a maybe I should not, yes, this is better. So this is not psi vector dot r naught vector, that's not the case. It's just, so the scalar psi, so negative psi times r naught hat, that is what the derivative of t hat is. So then plugging this into that value, and then noticing that basically this whole expression can be written as omega vector cross ri vector plus psi vector cross ri vector. So this orange term is just psi vector cross ri vector. So you can see how this happens, right? So this angle is theta, and then psi vector is just upwards, so it's along z hat, and then the angle made by psi vector and ri vector, that's just 90 minus, so pi by 2 minus theta I. So sine of that angle is just cosine, and that's why that. And then basically ri cosine is basically the distance from the vertical axis going through the center of mass, right? But anyway, you can basically write this orange term as psi vector cross ri, or psi vector cross ri vector. And then this pink term, or whatever purple term, that is just omega vector cross ri vector. So just do the whole calculation, you will see this works out, right? So you can write your velocity, the relative velocity, as omega vector plus psi vector and all of that cross ri vector. So we will also prove this for a general case, that even if your body is not a thin disk, or even if your r naught vector is not perpendicular to z hat, it still works, right? And then since omega vector is perpendicular to ri vector, you can figure out this purple term, this taking the cross product of ri vector on this purple term, right? So that's involved in the calculation of L vector. So we just want ri vector cross velocity vector, and that's why ri vector dot the first term, and using the triple product identity, so the vector triple product, you can just write it as ri vector dot ri vector, which is ri squared, and that times of omega vector. So ri square is a constant with respect to time, which is really nice. And that minus so the other term, which just becomes 0 because ri vector dot omega vector is 0. And then also you can let ri vector be ri xy vector, which is the xy projection of this position vector, I mean relative position vector, but yeah, just the xy position of that, the xy projection of that, yes. And then the z projection, so the sum of these two, right? And then putting that into this orange term, but then the ri vector cross multiplied, ri vector crossed with this orange term. So you put this equation into that, and then you finally get this thing. So that's just a calculation. Yeah, you can do it yourself. Fine. So finally we can write the angular momentum that we were looking for, right? So the second term in the angular momentum equation, we can write it as summation of mi ri cross vi. That will just be omega vector, and then the moment of inertia about the axis which omega vector is aligned with, right? So a moment of inertia about that axis, and then plus psi vector times moment of inertia about the psi axis, so the z axis basically. And that's why you can write angular momentum like this. Yes. So as you can see, there's two components, mr naught squared psi hat and I psi times psi vector, right? These two components are along the z-axis, and at the same time they are also time independent. That is, they are not changing with time, because I psi is a constant, right? And then psi vector is also constant, so the second term doesn't change, and then mr naught squared is constant as well. Yes, that is if your gyroscope is actually going in proper circular motion. And then psi vector once again doesn't change. So the first two terms are time independent, so their derivative with respect to time will be 0, and then that's why you only consider the time derivative of this term I omega vector. So a lot of times people skip this second term. They do take into account the first term, they just skip the second term. Second term should also be taken into account. I used to make that mistake myself, but now I can see why even if you don't take that term into account, it still works out, because in the end its time derivative is going to be 0. So while writing the torque angular momentum equation, this will get destroyed anyway. Right, so now let's go to the general case for this blue equation. So the next few pages are going to involve a lot of complex exponentials and going from one reference frame to another, figuring out how rotating reference frames work. So I suggest you should look into that first. But anyway, let's go to that. So general case, consider this ugly 3D body. So I'm saying ugly, but I mean it could be beautiful 3D body as well. It could just be a sphere or something, but any 3D body, right? So might as well consider an ugly 3D body, the worst case scenario. So this is just a 3D body rotating about r0. So a rigid body, I should say, rotating about r0 axis, passing through the center of mass, which itself, so by which over here this thing is for r0 hat axis, not the center of mass, right? And we are taking the center of mass to be stationary, but if you have a center of mass that is not stationary, you can just use this equation and then make it stationary, so take its point of view in the end, right? So that's why even though I said it's a general case, but to skip some unnecessary calculations, I'll just take the center of mass to be the origin. Okay, so this r0 hat vector, it is aligned with this omega vector, which is the angular velocity about this axis, and this axis itself is rotating about some other axis, so the z axis in this case, right? So whatever axis it is rotating around, you just take that as the z axis and set up coordinate according to that. So yes, we just have some more notation. So once again the similar kind of thing. Sorry, yeah, everything is very much similar. So you still have the relative velocity. In this case we should not even talk about relative velocity, just velocity. But then to keep up with the notation, I'll just use this curved v. So vi vector is just dri vector upon dt. So in the reference frame that we were given the whole system in, right? So I will refer to that as the original reference frame, and then we'll also be using some other reference frame, which is a rotating reference frame. But for now, let's just study what symbols we are using. So we are using this fancy v for dri vector upon dt, so it's just a velocity. Then psi is once again just d phi upon dt. Omega is just d theta upon dt, where I have not actually okay, it's not d theta upon dt because I have used theta for something else. So yeah, in fact we don't even talk about what omega vector really is. We just use that in the calculation in the end. Fine. So in the very end, in fact. Now this thing is r0 vector, and then its projection on the xy plane is r0 vector comma xy, and then the vector that is perpendicular to it, so basically r0 vector comma xy but rotated by 90 degree about the z axis, that will be just txy vector, so txy hat. Yes, and then you have the x and y vector. So yes, and for any particle on this rigid body, you can decompose your ri vector into an xy component and a z component. So here's some notation for that, and now we can start. So let's use complex numbers to present the xy component of Ri vector. So yes, this is very unusual, but I want to use this because it helps in understanding how rotation is working, and also how to go from one frame to some other frame. Yes, so Ri vector can be decomposed into a z component and an xy component. Now the xy component will further be decomposed into an x component and y component, but those collectively, if we use the Argand plane for the xy plane, we can just write that as Ri xy and e power I theta I. So theta I is just for that particular ith particle. Yes, so you have this thing. Now we can also put a vector. So the xy plane we can also represent that as a vector, and then multiply that by a complex exponential. So that will be allowed in this whole derivation. You cannot do that for the z coordinate, but you can do that for the xy coordinate, because you are representing xy points in xy as complex numbers. So complex numbers are also just vectors basically, and that's why a vector times a complex exponential will be allowed for the xy component, and we won't even need that for the z component. So yes, so theta I is the angle made by Ri xy. So this x component of the Ri vector, so the angle made by this projection with the x-axis, right? And that's how we can write it like that, so using the Euler's theorem. Fine. And of course the imaginary part of this thing will be the y coordinate, the real part will be the x coordinate. Yeah, you get the idea. So now let's go to the rotating frame. So what rotating frame are we talking about? This rotating frame will have its coordinate system as this. So the x-axis, we will replace that with r0 xy hat. So this vector. The y-axis will be replaced with txy hat. So this thing, and then the z axis is still the same, right? So it's basically just xy and z, these basis vectors, but then you rotate the whole thing by phi about the z axis, and you get this, right? Okay, then the position vector of this ith point as seen in the rotating frame, we will set that to be this thing. Okay, so theta I dash, this is just a new variable that's like the analog of what theta I would be, right, if it was viewed from this other frame. Yes, something like that. Does that make sense? I think it should, right? So theta I hat is just, sorry, theta I dash, that is the angle made by the Ri xy vector as seen in the rotating frame with the r0 xy vector as seen in the rotating frame, right? So the rotating frame's x-axis, right? And the z component is still the same, because yes, there was no change in the z-axis. Okay, then in original frame, so I missed a e, but whatever. In the original frame, position is Ri vector is equal to, so this whole complex number, we will just rotate that by e power I phi, because whatever the position in xy plane as seen in the rotating frame, the rotating frame itself has been rotated by phi from its initial configuration. So that's why whatever particle it sees, whatever position it sees, that is actually also having been rotated, but you can't see the effect because you yourself are also being rotated. And that's why the actual position will be Ri dash xy in the xy plane, of course, e power I, so theta I dash plus phi, that accounts for the rotation of this rotating frame. And then the z component is still the same, right? And now we can use Ri dash e power I theta I dash, that thing as Ri dash vector, but it should be in xy, sorry, right? So like that. So it's just the xy vector as seen in the rotating frame, right? Well, that times e power I phi So rotating that by phi anti-clockwise about the z-axis, that will give us the vector ri xy, so without the dash, as seen in the original frame, right? So as you can see, a vector times complex exponential. This might seem very useless, because why would somebody want to do, but in this particular case it's really helpful, because next we are going to differentiate this equation. So over there you will need this, instead of writing out the whole components, you can just do this thing, right? And then also you'll have to go back to the original frame in the end. So yeah, you will also need it for that, right? So differentiating this, you just get this thing. So using the product rule, on the first term you can split this, and then once again you just split the vectors into basically like two vectors. Yes. Oh, okay, this should not be here, because of course this plus this will be giving 2 times of that, so that's not correct. It should be like 0 over here or something. So I mean, yeah, but you get the idea. I mean, it's just this thing plus that. Hopefully that makes sense, right? And it should be 0 over here, sorry. Yes, does that make sense? Okay, now note that the first term, so the first term is just the velocity vi dash as seen in the rotating frame, but rotated about the z-axis by phi. So yes, I mean, the original vi dash would just be this whole thing, but without that e power I phi. But now that there is an e power I phi, you're just rotating this anti-clockwise by phi about the z-axis. But well, that thing is basically your original, I mean, if it was viewed by your original frame, right? So this vector vi dash xy comma viz, if that was viewed, this vector in the rotating frame, if that was viewed from the original frame, it would appear like this. Isn't that right? Yes. But we know that vi dash, that is just omega dash vector times r I dash vector. So here this omega dash, I just put that dash over here, so so as to represent that it is seen in the rotating frame. Yes. Yeah, so that would have been the thing, but then you are now seeing it from the original frame, and that's why it's just going to be omega vector cross ri vector. And what about the second term? So the second term is just representing this phi vector cross ri vector. So let's just go into that and see how that's happening. So ri dash is just, I mean, ri dash xy, it should be xy, sorry. So ri dash xy, that is just the position vector in the xy plane as seen in the rotating frame, right? Now that times e power I theta, sorry, e power I phi, that's just this thing seen in the non-rotating frame, the original frame. But then you're multiplying that by I phi, so you're rotating anti-clockwise about the z-axis by 90 degrees, but at the same time you're also multiplying by phi, and phi is also along just the z-axis. So it's essentially you are multiplying, you are rotating anti-clockwise by 90 degree about phi vector, and then also multiplying by the magnitude. So isn't it like the cross product? It is, right? It's just the phi vector cross ri dash vector. No, now it's going to be ri vector, because ri dash e power I phi ri dash xy, of course, e power I phi, that's seen in the original frame, that's just ri vector, right? So yeah, the cross product, so phi, I should say psi over here, this is supposed to be psi, not phi. Yes, so it's just of course it's just going to be psi, not phi, come on, everywhere it should be psi, right? So after doing that correction, yes, it's just the cross product with psi of your ri xy vector. So that's in the original frame now. So now we are done completely with the rotating frame, and then we just have these two terms in the original frame now. So this is represented by omega vector cross ri vector basically, and this is represented by psi vector cross ri vector. Come on, this is supposed to be psi. Why did I write phi everywhere? I don't know, but You get the idea, right? It's supposed to be psi over here. Yes. Okay. So yeah, and what about this 0? Well, psi is along the z-axis, so any z component, right, of our ri vector, that will get cancelled while taking this cross product anyway, so you don't need to worry about this 0, and then that is, yeah, it just works out. Cool. So now we have proved this for the general case as well, that we can just write the velocity vector of each particle as omega vector cross ri vector plus psi vector cross ri vector, where your omega vector is actually rotating with psi vector. So it's like superposition. Hope that makes sense. Fine. So that's it. I will see you guys in the next video.